everyone, and this is module 7 of the course Econometric Modelling. Till module 6, or rather in module 6, we discussed simple regression. So, that was the first module under part 2. Part 2 is on overview of classical linear regression model, and I discussed module 6 in the last session, where I dealt with simple regression, and there we discussed the method of ordinary least square regression, its mathematical interpretation as well as geometric interpretation. So, specifically what ordinary least square regression is all about, how it actually fits a line through a set of data and give us the estimates of the line. That was the purpose. Now, in this module, again on simple regression, we are actually going to discuss some of the features or characteristics of simple regression. The first thing that we are going to discuss is change of scale. Change of scale here refers to the fact that when we are changing the scale of measurement of y or x, then how it is going to impact the parameter estimates, whether it is going to impact the parameter estimates or not. So, change of scale of y or x does not actually alter the results, since the coefficient estimates will change by an offsetting factor to leave the overall relationship between y and x unchanged. So, this is actually explained below, that suppose our original model is y t equals alpha plus beta x t plus u t, and we replace y t with y t by c, where c is any constant. So, it can be say 100, it can be 1000, anything or any other number 25, 50. Then the equation becomes y t upon 100 on the left hand side, and right hand side is also divided by 100, and then breaking up we have alpha divided by 100, beta divided by 100 multiplied by x t, and u t divided by 100. So, you can see that when y t is scaled down by an amount say 100, then the parameter estimates are also scaled down accordingly. That is why the coefficients are scaled down accordingly with a change in the scale of measurement in y. Similarly, a change in the scale of x will only alter the scale of beta. If I replace x t with x t divided by 100 or 1000, then it will simply become the parameter estimates beta will become beta by 100 or 1000. So, other than that, no change is going to take place. Now, we take an example. In the table, estimates from the two regressions of annual gross bank credit to industry on annual call money rate for the period 1990 to 2018, taken from India. So, these are Indian data. We have collected data on annual gross bank credit to industry, that is our dependent variable, and call money rate is our independent variable, annual call money rate. So, we are trying to find out whether annual call money rate impacts the annual gross bank credit to industry or not. So, that is done with respect to two different scales of measurement of y, right. So, y once is measured in terms of billions of rupees, and the second one is millions of rupees. So, you can see that both these parameter estimates, intercept as well as call money rate, their values are same, just the decimal points or places have changed. So, here the decimal place has come 3 point before when we moved from million to billion, and similarly this has also changed by the decimal has moved 3 points to the left. So, here we had minus 943,589 and now we have minus 943.589, that is the only difference we can observe. So, this is an example which shows that with change in scale actually nothing changes, the values remain, the estimates remain the same, again only their scale of measurement changes. The next characteristic or feature that we will be talking about is linearity. In order to use OLS, a model has to be linear. This means that the relationship between x and y must be capable of being expressed diagrammatically using a straight line. More specifically, the model must be linear in the parameters, that is alpha and beta, but it does not necessarily have to be linear in the variables, that is y and x. So, now again I will show with example that how linearity in x and y or in variables can be resolved in most cases, while we certainly do not want non-linearity in the parameters. So, linearity in parameters actually means that the parameters are not multiplied together, divided, squared or cubed, etc. So, in case we observe any non-linearity in the parameters, that actually cannot be handled, or a model having non-linearities in the parameters cannot be estimated using OLS. Whereas, non-linearities when present in the variables can at times be estimated using OLS. I will now show you examples of that. So, models that are not linear in the variables can often be made to take a linear form by applying a suitable transformation or manipulation. For example, this model, the following exponential regression model, can be suitably transformed into a linear regression model. To begin with, we have y t equals a x t raised to the power beta e raised to the power u t. Now, if I take natural logarithm, then this becomes logarithm of y t equals logarithm of a plus beta logarithm of x t plus u t. And then if I call logarithm of y t is small y t and logarithm of a is alpha, similarly logarithm of x t is small x t, then we actually from this expression can get our original regression model, or generally the way we write it. So, simply y t equals alpha plus beta x t plus u t. Similarly, if we have a regression model like y t equals alpha plus beta 1 upon x t plus u t, then this can be estimated using OLS by setting 1 upon x t equals to z t. So, in that case this model will simply look like y t equals alpha plus beta z t plus u t. So, z t is a variable which is originally 1 upon x t. Now, converting 1 upon x t or renaming 1 upon x t as z t actually does not impact alpha or beta. So, my parameter estimates are untouched, and that is why this is an estimable model, right, and there is actually no harm in this kind of conversions when we can convert it into linear formats or just change the name of the variable from 1 x t 1 upon x t to z t. Our parameter estimates remain the same and these models are estimable using OLS. Now, we take another example in order to explain the interpretation of beta in the context of non-linearity in the variables. So, for example, an increase in education from 5 years to 6 years or from 11 to 12 years increases wage by say 8%, ceteris paribus, which implies that other things holding constant, if we have an estimate that with increase in education by 1 year, wages increases by 8%, then how are we going to write it? A model that gives approximately a constant percentage effect is actually log wage equals to alpha plus beta education plus u. In particular, delta u equals to, if delta u equals to 0, so all other factors contained in u and all of them are held constant, then a change in education is going to tell us how the percentage what will be the percentage change in wages, and that is given by 100 multiplied by beta. Since the percentage change in wage is same for each additional year of education, the change in wage for an extra year of education increases as education increases. In other words, it shows an increasing return to education. So, ideally increasing returns to scale is a concept in economics where it says that when the inputs employed in a production process increases and increases in certain proportion and output increases more than proportionately, then we call it increasing returns to scale. So, here we are observing increasing returns to education, that is with increase in education wage is increasing. So, and this increase is actually by an amount which is nearly 8%, right. Now, how we are able to comment on this? So, the coefficient of education has a percentage interpretation when it is multiplied by 100, that is wage increases by 8.3% for every additional year of education. This is because when we are measuring wage as logarithm of wage, then a change in logarithm of wage is actually logarithm of say W t minus logarithm W t minus 1, right. Or here it is probably better to talk in terms of individuals. So, we are considering individuals having different levels of education. So, I can write it as logarithm of W I and logarithm of W j. So, j has a different wage rate, I has a different wage rate, their education levels are different, and accordingly I am having different wages associated with them. Now, you know that this can be written as W I upon W j, and this is actually another way of measuring percentage changes or growths. Like growths are calculated either as W I minus W j divided by W j, or it can be logarithm of W I upon W j. So, the left hand side, that is logarithm of change in logarithm of W or wage, is actually measuring the percentage change in the wages earned, and this is changing because of a change in education of individuals, right. So, the coefficient of education has a percentage interpretation because of this reason. It is important to remember that the main reason for using the log of wage is to impose a constant percentage effect of education on wage. The natural log denoted by ln most often of wage is rarely mentioned. So, when we interpret or explain or we talk about the impact of change in education on wages, we actually do not say that with change in education by 1 year, log wage changed by 8%. We say that wages changed by 8% because that is inherently implied by the way we have framed the model. So, that is why it is not correct to say that another year of education increases log wage by 8.3%. Rather, we say that another year of education increases wage by 8.3%. Fine. Then we come up with a summary of functional forms involving logarithms. So, since logarithm is in some way converting or treating one of the variables or both the variables as nonlinear or converting nonlinearities into linearities, that is why logarithm as a special cases are mentioned here. This is also applicable when we measure elasticities, when we measure growths, then a lot of time we use logarithm in economics, and as a result of which a summary of functional forms involving logarithms are specifically mentioned here. So, the models could be like both of them are in levels. So, y is in level, x is in level, and we have simple interpretation of beta. X changes by certain unit, y changes by certain unit, or the change in y is given by the parameter estimate beta. The model could be level log, that is when y is in level and independent variable x is measured in terms of logarithm, then the interpretation of beta would be, you can see that since x is in logarithm, so this measures percentage change in x straight away, while this is simply change in y, and that is given by beta divided by 100. Log level, when y is measured in terms of logarithm, x is measured in its level. The example that we had just taken, the example of the impact of education on wages. Then we have percentage change in y as measured by 100 multiplied by beta, and y, and that is given by a change in x. So, delta x, that is a change in x, changes percentage changes y by beta multiplied by 100 times. And finally, we can have log. So, y is measured in terms of logarithm, x is also measured in terms of logarithm, and then again beta has the usual interpretation that percentage change in x leads to beta percentage change in y, right. So, this is the summary of functional forms involving logarithms. However, some models are intrinsically nonlinear. For example, this is a model which is intrinsically nonlinear. So, here first of all we note that there are 3 parameters that needs to be estimated: parameter alpha, parameter beta and parameter gamma, right. We have only 2 variables yt and xt. So, first of all, unless and until I know the value of gamma, I cannot come up with the variable xt raised to the power gamma. We can linearize it partially by writing it as logarithm of yt. Of course, it should be also supported by a theoretical argument under economics or whatever field from where we are taking the example or putting the or fitting the model in. So, this can be logarithm of yt, logarithm of alpha plus beta xt gamma plus ut. Okay. And this actually does not solve any problem, and as a result of which we cannot, this actually remains unestimable or an intrinsically nonlinear model. Now, that is why we say that such models cannot be estimated using OLS, but might be estimable using a nonlinear estimation method. Another example of nonlinearity in parameters could be this example, where consumption is expressed as a function of 1 upon alpha plus beta multiplied by income plus u. So, I cannot come up with a variable involving income which is the independent variable unless and until I know the values of alpha and beta. So, this is another intrinsically nonlinear model which is not estimable using methods like OLS, where it is required to have a linear relationship between the parameters, right. Certain nonlinearities in the variables can be converted into linearity. Okay. The next thing that we talk about is the goodness of fit. It is useful to compute a number that summarized how well the OLS regression line fits the data. So far we have talked about obtaining values of alpha and beta and fitting a line. There are lot to discuss, lot more to discuss about how these parameter estimates are, but a basic starting point is that how the model fit is, how good the line fit is. So, each yt can be written as a fitted value plus the residuals, right. So, I had probably explained it in a previous module that yt hat is actually alpha hat plus beta hat xt. So, the estimated part of yt is denoted by yt hat, and what remains is the residuals, which is ut hat. Residuals are separate from error terms, I repeat. Now, we define total sum of squares denoted by TSS, explained sum of squares denoted by ESS, and residual sum of squares denoted by RSS, as TSS is yt minus y bar whole square summed from t equals 1 to capital T. ESS is yt hat minus y bar whole square summed from t equals 1 to capital T, and RSS is ut hat square again summed from t equals 1 to capital T, where TSS is equal to ESS plus RSS. This is something we are going to prove in the next slide, but before that I need to tell you that you note TSS is total sum of square. Now, what is the sum? The sum is actually the deviation of the actual observations from the mean value, the mean of the series y. Explained sum of square is again, what is the sum? The sum is actually the deviation of the estimated values from the mean values of the series, again the YT series, and RSS or residual sum of squares simply considers the squares of the residuals and sum them up, right. Now, I prove that TSS equals ESS plus RSS. It is actually pretty simple. What we do is, first of all we define TSS. We have already defined TSS. So, TSS is YT minus y bar whole square. This is actually broken into two components, YT minus YT hat plus YT hat minus y bar. So, if I remove these brackets, you can see that the YT hat and this YT hat, they would cancel out. So, this simple expression is actually expanded here by incorporating 1 minus YT hat, 1 plus YT hat. Again we have the square. Now, we expand it following a plus b whole square formula. So, before that this YT minus YT hat is replaced with UT hat, because you remember YT was written as YT hat plus UT hat, right. So, YT minus YT hat would be UT hat. YT minus YT hat is replaced with UT hat. Now, when I expand it and then take separate summation, then I have UT hat square 2 UT hat into YT hat minus y bar and then YT hat minus y bar whole square, separate summations. So, this is simply RSS the way we have defined RSS. This is simply ESS the way we have defined ESS in the previous slide. So, I am left with this expression, and this expression is equal to 0. Why? Because if I take this summation UT hat into YT hat minus y bar can be written as summation UT hat YT hat minus summation UT hat y bar. So, first of all you can see that y bar is a constant. So, this expression will become y bar into summation UT hat, and summation UT hat is 0. So, this term becomes 0. And if I expand this expression, then we have summation UT hat into alpha plus beta x t, alpha hat plus beta hat x t. Again, by breaking it, I will be having summation UT hat alpha plus summation UT hat beta hat x t. Now, note that alpha is constant. So, again since UT hat is equal to 0, I will be having this term equals to 0, and this term will become beta hat summation UT hat x t, right, and this term is 0. That is because of one of the assumptions of classical linear regression. That is something which we are going to take up in the next module. For the time being, I tell you that this multiplication is 0 because we assume independence between the residual and the independent variables, or the error terms and the independent variables. So, as a result of which this entire expression becomes 0, and consequently I have TSS equals RSS plus ESS. It has been proved. Now, we are going to define the goodness of fit measure. So, R squared of the regression, also known as the coefficient of determination, is actually a goodness of fit measure, that is, it measures how good the model fit has been. Now, R square is defined as ESS upon TSS, explained sum of square divided by total sum of squares, and the expressions are mentioned here. So, R square actually measures that what percentage of the total sum of square is actually explained by the fitted line. Alternatively, r square can be written as 1 minus RSS upon TSS. So, this is the same thing, residuals sum of square divided by TSS gives us that what percentage of the model is not explained by the line, and 1 minus that gives us what explained by the line, and this is the expression for r square. So, these are the two alternative expressions. R square is the ratio of the explained variation to the total variation. Thus, it is interpreted as the fraction or percentage of the sample variation in y that is explained by x. The values of r square is always between 0 and 1 because ESS cannot be greater than TSS. So, explained sum of square cannot be greater than total sum of square because just now we have proved that explained sum of square plus RSS, residual sum of square, they add up together to form TSS, and all of them are positive numbers because all of them are squared sums. So, once I take the square, then anything negative even becomes positive, and when we sum them up they cannot be negative numbers. So, individually all of them are positive numbers, two positive numbers sum up to make TSS, as a result of which TSS, RSS, ESS all positive, and that is how ESS upon TSS can never be less than 0. That is how r square value always lies between 0 and 1, it is a fraction. If the data points all lie on the same line, OLS provides a perfect fit to the data. In this case, r square equals to 1. If the line fit is perfect, that is, any deviation from y to its main value is completely explained by the fitted line. So, y t minus y bar whole square and summed up is equal to y t hat minus y bar whole square and summed up, they are the same, then r square becomes 1. A value of r square that is nearly equal to 0, that is the other opposite extreme case, then it indicates a poor fit of the OLS line. Very little of the variation in the yt is captured by the variation in yt hat. So, basically the difference between yt and y bar is hardly explained by the very difference between yt hat and y bar. Then we have a case where r square is actually close to 0. In rare cases, we wish to impose the restriction that when x is equal to 0, the expected value of y is 0. So, now we are actually talking about a special case where the regression is through origin. In this module, we are discussing certain characteristics of simple regression. We started with change in the scale of measurement, then we talked about linearity, then we talked about goodness of fit measures, and the final thing that we are discussing is regression through the origin. So, in rare cases, we wish to impose the restriction that when x is equals to 0, the expected value of y is 0. There are certain relationships for which this is reasonable. For example, if income is 0, then income tax revenues must also be 0. So, in that case we cannot have, or we need not have, a positive or negative or inclusion of an intercept or constant term. So, we simply write it as y tilde equals beta tilde x, right, and this is the deterministic component. For a random component we can add certainly a u here. Now, this is called a regression through the origin, where beta tilde is the slope estimator. Beta tilde solves the first order condition x t into y t minus beta tilde x t summed up from t equals 1 to capital T and sets equal to 0. So, when we had two parameters to be estimated, then we had two first order conditions, and when we have only one parameter to be estimated, we have only one first order condition. And from this first order condition, beta tilde is solved as summation x t y t upon summation x t square, t running from 1 to capital T. So, this is a regression through the origin, and these are the books that I have followed in order to come up with the or present the content of module 7. Thank you.